Assalamualaikum. Today our group will discuss about topic 12, which is memory management. Memory management is the process of organizing and controlling a computer memory. It allocates memory to programs when they need it and print it when they are done. This ensures efficient use of memory, smooth system performance, and support multitasking. The purpose of memory management is to ensure memory is used efficiently, prevent waste, and allow multiple programs to run smoothly at the same time. It also keeps programs separate so they don't interfere with it. Memory management is important for multitasking, maintaining system security, and detecting errors like anomalies. It ensures the computer program perform well and protects sensitive data from unauthorized access.
So, what is key technique in memory management?
There are several key techniques in memory management. First, partitioning, which divides memory into sections. Fixed partitioning use equal size blocks, while dynamic partitioning adjusts each size based on the program needs. Next is paging, which breaks memory into small fixed-size blocks called page. Programs are also divided into page and storing available memory space, making it more efficient. Another technique is segmentation, which divides memory based on logical sections like function or data. This makes it easier to manage, though it requires more effort to track. Clean memory is another important technique. It allows the computer to use part of the hard drive as extra memory, helping large programs run even with limited RAM. However, overusing it can slow down the Next is memory allocation, which involves assigning memory. Static allocation assigns it once, while dynamic allocation adjusts during the program's runtime, making it flexible. Other than that, garbage collection automatically clears memory that programs no longer use, preventing memory throttling. Finally, compaction gathers clear memory into one large block, making it easier to allocate memory for larger tasks. To share, memory management is essential for a computer to run efficiently and handle multiple tasks. It ensures memory is used sparsely, prevent errors, and keeps the system secure. Understanding this technique can help us better appreciate how computer works behind the scenes.
So now, I will be talking about paging and segmentation. So, paging divides memory into pieces-sized blocks called pages. These pages can be stored anywhere in the memory, making it easy to manage. When the program runs, it's broken into pages. Each page fits into spaces in memory called frames. If the last page isn't full, it just takes out what it is. However, segmentation is a little bit different from pages because segmentation divides memory into variable size segments based on logical units, which is functions or arrays. Unlike paging, segments can be different in sizes, and each segment is managed using a table that keeps track of where they start and how long they are.
Oh, so what are the advantages of paging?
So, for paging, there are a few advantages that we can highlight. For the first one, it is simple management. This means the process of managing the memory is easier and it reduces fragmentation. And next, pages can also be easily moved in and out of memory, making it easy to swap. However, for segmentation, there are also a few advantages that we can highlight. For example, flexible organization. So, what I mean by segmentation can create flexible organization is because segments can grow independently, making it easier to manage data. On top of that, each segment can be protected separately, which can heighten the security. However, both the paging and segmentation of course have their own faults. For paging, these faults can happen. If a page isn't in memory, it can slow down performance while it loads. Other than that, unused space within pages can lead to wasted memory. This can lead to internal fragmentation. For segmentation, a few challenges that we can pay attention to is the risk of external fragmentation. This can happen because of free memory that can become scattered, making it hard to find large enough spaces for new segments. Additionally, managing segments of various sizes is more challenging than managing fixed-size pages, considering segmentation is a variable-sized memory.
So now let's talk about the virtual memory. By combining physical RAM with secondary storage, such as a hard drive or SSD, virtual memory is a memory management approach that gives the appearance of a huge continuous memory area. It permits the execution of processes in the event that the system lacks the physical memory necessary to hold them all simultaneously. Role in multitasking for virtual memory are process location. So virtual memory ensures that each process operates in its own virtual address space, preventing interference between processes and increases stability. Next, efficient resource allocation. By swapping inactive data or parts of a process to secondary storage, virtual memory allows multiple programs to run simultaneously, even on systems with limited RAM. Next, concurrency. Processors can share the CPU and memory without exhausting physical RAM, ensuring smooth multitasking. Next, ease of development. Developers can write programs assuming large amounts of memory, as virtual memory abstracts physical constraints. For example, a user can simultaneously browse the web, edit documents, and also stream music, even if the combined memory requirement exceeds physical RAM.
So, what is demand paging?
Okay, thank you for the question. What is demand paging? Demand paging is a technique used in virtual memory systems that locks memory pages into RAM only when a process requests them. The operating system loads only the necessary pages into physical memory rather than loading the whole program. So how it supports virtual memory? First, it optimizes memory use, which is only active parts of a program reside in the RAM, saving space for other process. Second, faster process startup. Programs begin execution without waiting for the entire process to load into memory. Third, page swapping. When physical memory fills up, inactive pages are swapped to secondary storage, freeing RAM for new pages. And last one, page fault handling. If a program accesses a page is not in the memory, a page fault occurs. The OS fetches the required page from disk, allowing process to continue execution. For example, a video editor may not load editing tools into RAM initially. When the user opens the color grading module, its pages are fetched into memory via demand paging.
What about the system that use virtual memory?
Thank you for the question. The examples of systems that use virtual memory as effectively, first is Windows operating system. Windows use a paging file stored on the disk to manage virtual memory. The OS dynamically moves inactive pages to this file, allowing seamless multitasking. For example, a user can run a video conferencing app, a large Excel file, and a web browser with multiple tabs, even on a system with only 8 GB of RAM. Second, Linux operating system. Linux use a swap partition or file for virtual memory. Administrators can fine-tune the swappiness parameter to optimize system performance. For example, a server running database queries, web services, and background tasks efficiently manages memory with swap space. Android. Android employs virtual memory techniques like ZRAM, compressed RAM, which is compressed RAM, and swapping to optimize memory usage on mobile devices with limited RAM, such as a smartphone, running resources-heavy games while keeping messaging apps and music players active in the background. Last, iOS. While iOS limits background activity to preserve battery, it still employs virtual memory to manage resources efficiently. An example, a user switching between editing video, browsing the web, and also checking email experiences minimal performance lag due to efficient virtual memory management. These examples highlight how virtual memory enables multitasking, efficient resource use, and smooth application performance on a variety of platforms.
Now, I'll be talking about memory management and its importance in modern computing. Memory management is an essential facet of how everything works smoothly. Let me take you through some real-world application of these concepts. Let's start with operating system. You understand that it is possible to have several applications running simultaneously, as when browsing the internet and listening of music at the same time. For example, we edit documents and all during the same time. It is all thanks to memory management. Techniques like virtual memory and paging allow the system to allocate RAM efficiently, so everything runs smoothly without freezing or crashing. Okay, next, think about mobile applications like Instagram or WhatsApp. You ever wonder how these apps work without making your phone slow down when providing multiple functions? That's where memory management comes in. Techniques like garbage collection automatically free up spaces and unused memory, ensuring that your apps don't consume excessive resources and crash when you are multitasking.
How about other applications like gaming?
Now, let's move on to gaming. Imagine playing a high-performance game with stunning graphics. Games have dynamic memory allocation, which allow large textures and assets to be loaded efficiently. This ensures a smooth and immersive gaming experience without lag. It's why your favorite games do not crash in the middle of a crazy action sequence. We also see memory management in embedded systems like smartwatches and IoT devices. These gadgets generally have very small memory, but memory management allows them to complete multiple user tasks of a wide range, such as your smartwatch may look at your heart rate, show notifications, and execute new applications simultaneously thanks to its mastery of the memory management. Lastly, in cloud computing, memory management is a vital. Clouds such as AWS or Microsoft Azure also utilize it to randomly distribute memory content among the virtual machines. This enables companies to manage dynamic workloads effectively, thereby efficiently utilizing resources and decreasing costs. And without it, those big systems like cloud platforms would run with so much less reliability. So, to summarize everything, memory management is the art and science of effectively using resources such as RAM, ensuring the stability of the system and scalability of the device to respond to needs of the users. It's the backbone of the modern technology. In conclusion, memory management is indispensable in our world today. Operating systems, mobile application, gaming, embedded system, and cloud platforms, to name a few, guarantee unimpeded performances. We would have frequent crashes, sluggish system, and efficiencies in the technology we use today. For example, thank you so much for listening. I hope that this has provided you with an improved notion of the importance of memory management to our everyday life. Thank you.